Sorry, I just started to record the lecture. So concrete is made by several major components. Okay, so the most important thing is Portland cement, which is the fine powder we can buy in bags from Home Depot or Lowe's. Okay, if we mix Portland cement with water, we will have a so-called cement paste. Okay, if we add sand to cement paste, we will have mortar. Okay, and we'll use mortar to glue the masonry, the bricks together. And the concrete is combination of mortar, which including cement, water, sand, and coarse aggregate, which is larger stone inside the concrete. So the major component in concrete is cement, water, sand, and coarse aggregate. We also have some small percentage of air, typically about 1 to 3% by volume. Okay. So air is introduced to concrete for some reasons. For example, to enhance the durability of concrete. Okay, we're going to talk about that in future lectures. But the major component is cement, water, sand, and coarse aggregate. So here is some of the basic famous structures made by concrete. This is Baha'i Temple in Illinois. Okay, and this is the Baha'i Temple in New Delhi in India. We can see the color of the concrete is white, which is called white cement concrete. The color in typical concrete is gray color. It is caused by the ferrite oxide in the concrete. So white concrete is a concrete without ferrite, so the color is white. Okay. So the picture on the left is the Millau Bridge. It's used to be one of the highest bridge in the world. And this is the Kuala Lumpur Twin Tower. Okay, so again, it is one of the highest building in the world. Currently, the highest building in the world is the Khalifa Tower in Dubai. Okay, the height is 27,000 feet. Okay, the cost of a building is around 10 billion US dollar. Right. So concrete can use in all type of infrastructures, including road, bridges, buildings, dams, and so on. Okay. And here is comparison of the major property of concrete with other type of building materials, including aluminum, steel, wood. Okay. So for concrete, the density is around 23 to 2400 kilogram per cubic meter. So it is much lighter compared to steel, similar to the density of aluminum. Okay. So concrete is kind of strong under compression, but much weaker under tension and shear. Okay. For normal concrete, the compressive strength is around 30 to 40 megapascal. Okay. The tensile strength is around 10% of the compressive strength, which is around 3 to 4 megapascal. Okay. But for high performance concrete, we can enhance the strength to more than 100 to even 200 megapascal under compression. Okay. The elastic modulus of concrete is around 25 to 30 gigapascal, also much lower compared to steel. The coefficient of thermal expansion of concrete is very similar to steel. This is a very important property for reinforced concrete structures, because the thermal expansion coefficient of steel and concrete are very similar. So when we have a temperature change, we will not have a debonding between the interface between the steel and the concrete. Okay, so otherwise, basically we cannot make reinforced concrete. The conductivity of concrete and also the fabrication of concrete is also much lower compared to steel, okay, as we can see from here. And the cost of concrete is about 5% of the steel structure. Okay. So the pros and cons of concrete. Concrete, if designed well, could be last hundreds or even 1,000 years. As we will see in a moment, many ancient concrete from ancient Egyptians or ancient Roman is still here. Okay, concrete can be very, very durable. The cost of concrete could also be low, especially compared with steel. And the concrete can be formed on site. So typically we need to set up the formwork, and we mix fresh concrete in a concrete truck, and then we pour the concrete in the formwork. So it is very energy efficient. Concrete is also inflammable, so it's very resistant to fire and also thermal resistance. Okay. On the other hand, steel is not very thermal resistance. Okay. And concrete is also water resistance. It does not afraid of water, especially for well-designed concrete. But the concrete is very brittle, which means under tension and shear, it is pretty weak. Concrete also has a slow material development. The strength of concrete will be achieved after several days. Okay, after 1 day, you can detach the formwork. After 7 days, the concrete will be strong enough, and after 28 days, the concrete achieve its final strength. Okay, so you need time to develop its strength. Also, concrete is kind of heavy, so it has a low strength to weight ratio compared with steel. And also, because concrete is formed on site, we need to set up the formwork. It will take some time, and also labor, and also the cost. So this is a kind of drawback for concrete. And lastly, concrete has the problems called volume instability. Okay, for some concrete, it may shrink or creep. We're gonna talk about shrink and the creep of concrete in future lectures. But if that happens, concrete may crack under different conditions. That will reduce the strength and also durability of concrete. So we should watch for volume instability for concrete. Right. So we just mentioned concrete can last 1,000 years. This is ancient Egyptians. They built the famous pyramid 5,000 years ago. Used their concrete. We're gonna talk about their chemical reaction for the ancient Egyptian concrete in a moment. Around 2,000 years ago, ancient Roman engineer they used their concrete to build the famous Colosseum and the Pantheon. Okay. And here shows why we should put reinforcement or rebar in a concrete specimen. Okay. If the concrete beam, in this case, has no steel rebar, because concrete is very weak under tension, so the bottom tend to crack earlier under this load. Okay. If we put steel rebar in the areas where the concrete will experience tension load, so the rebar will take most of the tension load. As a result, the reinforced concrete beam will take much more moment compared with the plain beam. Okay. All right, I here talk about pre-stressed concrete. I think some of us has take about pre-stressed concrete design in your class. Here is the general review of why we should put the pre-stressed rebar in concrete. The first case is a typical bending moment for concrete under the load in the middle of span. Okay, this is the moment diagram. Before we take the load for the beam, if we apply pre-stress tension in the rebar, which is in the bottom section of the beam, then the moment diagram before the beam take a load will be something like this. So the beam will be bending upwards. Okay, so if we do that, after the load is taken, the net maximum load will be lower compared to the first case. So we reduce the maximum load the beam will take by applying a pre-stress in the rebar. Okay, so this is the reason why we put the pre-stress rebar in concrete. Right. So in this class, we also talk about different innovations in concrete, including shotcrete, pumping concrete. We talk about self-consolidating concrete, which is a concrete does not need any type of consolidation. So typically when we pour the concrete in the formwork, we need to consolidate to get rid of the air, so to make the concrete smooth and strong. Okay. We also need to cure the concrete. We need to cover the concrete, use plastic sheets, or provide water, so we call that curing. There are some special curing technology, including steam curing, or even curing use microwave. Okay. We're going to talk about that again. We also talk about admixtures, including silica film, flash, and also superplasticizer, or air entraining agent, or shrinkage reducing admixtures. Okay, so we put these admixtures in concrete to enhance certain type of performance. Okay. We also talk about different type of aggregate. Again, aggregate is the sand and the coarse aggregate, larger stone in concrete. So that's a different type of aggregate we can use in the concrete, including lightweight aggregate and also recycled aggregate. Okay. We're going to talk about latex and why and how we can put a polymer in concrete to modify the performance, or even fibers in concrete. Okay. So this is things we're going to cover in future lecture in this class. So when we look at the concrete in macro scale, we see concrete as homogeneous materials. Okay, if we look at the concrete in millimeter scale or centimeter scale, we know concrete is made by cement paste, sand, and coarse aggregate. But if we put the concrete under microscope, it will show something totally different. Okay, in the future lectures, we're going to talk about the microstructure of concrete, such as turboremerite and CEE688 sheets. Okay. So to study the performance of concrete in the macro scale, we need to study the concrete under micro and meso scale, so we can better understand the materials, so we can better design and make sure the concrete will perform based on our requirements. All right, so this is the general introduction of concrete materials. The next part of this lecture, we're going to talk about cement chemistry. Okay. So cement chemistry including what is the manufacturing process of cement. So what are the materials we use to make cement? The major composition of cement, and also different type of cement. There are 5 different types of cement depending on the chemical composition and the type of applications. And also special cement. Okay. All right. Before we talk about modern cement and concrete, let's look at ancient concrete. So this is ancient Egyptian concrete. It's made by calcinating impure gypsum. So gypsum is calcium sulfate with 2 parts of water. So if we heat the gypsum in high temperature, okay, the gypsum will decompose into calcium sulfate with half water plus some of the water will be released. Okay, we call calcium sulfate hydrate. So this material can be ground into powder form. Okay. For the next chemical composition, calcium sulfate hydrate in the powder form will mix with water again, and it will form gypsum again. Okay. So gypsum has a certain strength. It is much weaker compared to modern concrete, but is strong enough to build the pyramid. Okay. So this is the basic chemical reaction for ancient concrete used by Egyptians. For ancient Romans, they use a so-called lime mortar or air mortar. So calcium carbonate, this is, limestone. So heated limestone into 1,000 degrees Celsius. As we can see, this is much higher degree compared to the ancient Egyptian use. Okay, so limestone will decompose into calcium oxide. We also call that lime, plus CO2. Okay, so calcium oxide is grounded into powder form. Again, mixed with water, and we have calcium hydroxide. Okay, and the calcium hydroxide will react with CO2 coming from the air. It becomes limestone again, becomes calcium carbonate again, and also some water will be evaporated. Calcium carbonate limestone will be stronger compared to the gypsum. Okay, so the Roman concrete is stronger compared to the concrete used by ancient Egyptians. Okay. All right. Both these 2 types of concrete, we call that non-hydraulic cement. The reason for that is because the end product, the gypsum, and also the limestone is not insoluble to water. So over time, they can dissolve by water. Okay. So non-hydraulic cement, such as these 2 concrete we just discussed, the product is formed by carbonation, but is not totally resistant to water. Okay. But sometimes they can make water resistant by adding pozzolanic materials. Okay. We'll talk about what is pozzolanic materials in a moment. Hydraulic cement, on the other hand, is hardened by reacting with water, and the final product is water resistance. And Portland cement, which is the name for modern cement, so everybody use Portland cement now, is a type of hydraulic cement. Okay, it is made by pulverizing, which is grounding clinker. So clinker is the product which is we're going to talk about in a moment, consists of hydraulic calcium silicates. Okay. So a little bit of history about modern hydraulic cement. The first natural hydraulic cement is found in England, so in 1796, is made by calcinating nodules of impure limestone containing clay. So limestone plus clay. Okay. So in limestone we have calcium oxide, and in clay we have silica and aluminum oxide. And in 1813, a French chemist, Vicat, produced artificial hydraulic lime, okay, together with limestone and clay. Okay. So modern cement is called Portland cement. It's patented in 1824 in England. Okay. So it's by calcinating limestone, also with clay. Okay. For cement, remember two major components. We need limestone and clay. Okay. You may wonder why we give a name Portland cement to our modern cement. The reason is simply as this. So the picture on the right is a quarry stone, which is coming from a small isle from Portland in England. Okay, the color of the stone in Portland, which is not in the US, in England, is very similar to the color of modern cement. So that's the reason why we call modern cement Portland cement. Okay, so it's not coming from Portland. Okay. Right. So next, let's look at the manufacturing process of Portland cement. Okay. So the first step is we need to get the raw materials. We need lime, which is calcium oxide. We need iron. Okay. We need silica, and also we need aluminum. So these are the four major oxides in concrete. To help you remember that, take the first letter of the four words, that's LYSA, Lisa. Okay. So we need to get the raw materials from either quarries or from some other source. Okay. Then we need to burn all these raw materials in the big oven. We call that clinkering process. So that's the burning process. And after that, we get a so-called clinker. So the clinker looks like a charcoal. The size of clinker is around 1 or 2 inch. So we need to further grinding the clinker together with gypsum to get Portland cement powder. Okay, so let's look at the details of this process. So first, we need to get the raw materials. We need calcium oxide, which may come in from all these different sources. Okay, so most commonly source is limestone. So we get limestone quarry, we get calcium. It can also come from cement kiln dust or slag. Okay, so slag is a byproduct of steel manufacturing process. And this is an industry byproduct. So we can use the waste materials such as the slag to replace limestone if we can. The second one is iron. Okay, most likely will come in from clay, the natural source, and also some other source. We also need the third one, silica oxide, coming from clay. Okay. Flash, which is also called coal ash. This is the end product of the coal burning process. Okay, so this is another waste materials from industry, and also slag also have some of the silica inside it. Aluminum can also come in from clay, flash, or slag. Okay. So these are the four major products, four major oxide. The final major product we need for Portland cement is sulfate. Okay, it will come in from gypsum most likely. The reason we need gypsum in Portland cement is to slow down the chemical reaction of calcium silicate in clinker with water. Without gypsum, the chemical reaction will be too fast. So we do not have enough time to mix the concrete, transport the concrete from the plant to job site, pour the concrete, finish the concrete, and so on. We need at least 2 to 4 hours for this process. So we need to slow down the chemical reaction. So gypsum is to help us slow down the chemical reaction of clinker. Okay, again, we will talk much more about this. All right, so this is a video showing us the major chemical compounds in modern Portland cement.
Portland cements are manufactured by a process that begins by combining a source of lime, such as limestone, with silica and alumina, usually from clay, and a source of iron oxide, such as iron ore. The selected raw materials are then crushed, blended, and burned in a kiln to produce clinker. Once cooled, the clinker, with a small amount of gypsum added to regulate the setting time of the cement, is ground in a mill to produce the extremely fine gray powder called Portland cement.
All right, so again, the first step is we get raw materials from the quarry, most likely. Okay, so the stone from the quarry is first reduced to smaller size. Okay, and then they will be stored separately. Okay, as we can see from here. And the next step is the raw materials, including limestone, the sand, clay, and iron ore, are grounded into powder form and blended depending on the requirement. Okay, depending on what type of cement we want to make. Okay, so for this second process, we have dry process, which means no water is added during the grounding process. We also have the wet process, which is kind of old process. So water is added in the grinding process, but because water will be dried out for the third step, which is clinkering. So the wet process will need much more energy compared with the dry process. So in modern cement manufacturing process, typically the dry process is used. Okay, so dry mix of these raw materials and also they are blended. Okay, and then the next step is we put the raw materials into the kiln, KIL, which is a big oven with a certain slope. The size of the kiln is very big. It is slowly rotate. Okay, so the raw materials will go from the higher end slowly to the lower end. At different locations, different chemicals such as C3S, C2S, C3A, and C4AF, these are the major compounds in cement, will be produced. Okay, so at the end of this kiln, the lower end, we have clinker. Okay, the clinker will together combine with gypsum. Okay, the gypsum again is to control the chemical reaction. So in the video it said reduce the setting time. The setting time is how fast the fresh concrete set. Okay, so gypsum together with the clinker is grounded in step 4 into the fine powder form. Okay, and they will be stored, put in the truck, in bags, packaging, and they will be shipped. Okay, so these are the 4 major steps to produce modern Portland cement. So here shows a picture of the quarry. We need to gather raw materials such as limestone, okay, and clay. So the stone will be crushed into smaller size. So this is the crushing. And different raw materials will be blended after grinding. Right, so here's the overview of the cement plant. Okay. As you can see, the raw materials is blended and storage. Okay, raw material is grinding, and here is the kiln, which is slowly rotate. Okay, after we get the clinker at the lower end of the kiln, then the clinker will be transported. This is clinker storage, and together with gypsum, we have the cement grinding. Okay, so this is the overview of Portland cement plant. Okay. All right, so this is the kiln. The slope is pretty small. It's not very steep, but the size of the kiln is huge. Okay. Right, so this is the close-up of the kiln, the big oven. The temperature inside the kiln is very, very high. Okay, so more than 1500 degrees Fahrenheit. So to produce cement, we need a lot of energy. It will also generate a lot of gas because limestone and clay will decompose, release a lot of dust, release a lot of CO2, okay, green gas. So actually, the total man-made CO2, the greenhouse gas, around 7 to 10% is coming from cement production. Okay, so one of our major goals in the research lab here at the UH is how we can make the concrete greener, which means how we can reduce the footprint of concrete by using recycled materials. Okay, because cement will generate a lot of CO2. For every ton of Portland cement, it will generate 1 ton of CO2 gas. It's not 1 cubic meter of CO2 gas. It's 1 ton of CO2. Okay. And also a lot of energy is consumed. Okay. Right. So now generate a lot of pollution, use a lot of energy from the manufacturing process of cement. Sure. Here is an overview of the procedure. Okay, first of all, raw materials including limestone is crushed, clay and shell, which has silica, aluminum, and iron. Okay, calcium oxide is coming from limestone, so we need LiSA or Lisa. Okay, so they are grinded, stored, and final grinding between to put into a kiln. Okay. So after the kiln, we have clinker. The clinker will further grind it with gypsum. So we have Portland cement. Again, the function of gypsum is to slow down the chemical reaction, increase the so-called setting time of concrete. Right. Here is the detailed view of the kiln. Okay, so the raw materials will feed from the upper end here. Okay, so raw materials feed here. First of all, free water, clay will be released. Clay will decompose, release CO2 and other gases. And we call that dehydration zone. Okay, different zones has different temperature, as we can see from here, from low temperature in the upper end to the high temperature in the lower end. Okay. Also, we have calcination zone. In the calcination zone, limestone will decompose, and we have initial formation of compounds, including C2S. Okay, we're gonna talk about T2S and C3S in a moment. Okay. Then formation of melt. Melt is other major component in cement, and also C3S. Okay. So here's a picture of clinker. Looks like a charcoal. The round shape. The size is similar to the stones in concrete, around 20 meter or 3/4 to 1 inch. Okay. The gypsum is here shown on the right picture. It's kind of whitish color. Alright, so another video about delivery of cement.
Portland cement is available as a bulk powder or in waterproof bags. Most Portland cements are shipped in bulk using closed tanker trucks, covered rail hopper cars, rail tank cars, covered barges or ships with closed compartments. Pneumatic loading and unloading of the transport vehicle is the most popular means of handling bulk cement.
Okay, so there's many different ways to deliver cement, including numerical loading. Okay, this is for bulk storage. Okay, and also, of course, we can put cement in bags, like we buy the cement in bags from Home Depot. Okay. Here is how we can store cement. Okay, so make sure cement will not touch with water before we use it. Okay.
Portland cement is a moisture-sensitive material. If kept dry, it will retain its quality indefinitely. Cement stored in contact with damp air or moisture sets more slowly and has less strength than Portland cement that has been kept dry. The relative humidity in a warehouse or shed used to store bagged cement should be as low as possible. Cement bags should not be stored on damp floors but should rest on pallets. Bags should be stacked close together to reduce air circulation, but should never be stacked against outside walls. Where a shed is not available, bags should be placed on raised wooden platforms at least 4 to 6 inches above the ground. Waterproof coverings should fit over the pile and extend over the edges of the platform to prevent rain from reaching the cement and platform.
So before we mix concrete with water, mix cement with water, we should keep the cement dry. So as soon as cement is in touch with moisture, chemical reaction we call hydration will take place. Okay, so keep the cement dry before we use it is very important. So this slide is very important. Okay, so showing us what are the major constituent materials or the major oxides, as you can see from here, okay, in modern Portland cement. We have lime or CaO, calcium oxide. So we have a shorthand for calcium oxide in this class. So for cement chemistry, we use C for CaO. The reason for that, if we write all the chemicals in the full format, the name will be too long. So we use shorthand instead. Okay. So silica is SiO2. The shorthand is S. Okay, remember S in cement chemistry is for silica oxide. It's not for sulfur. Okay. Here also show a typical weight. Depending on the type of cement, the percentage for different oxide will be different. Okay. The third one is aluminum oxide, alumina. Okay. Al2O3, the shorthand is A. Okay. Ferric oxide, Fe2O3, shorthand is F. Also, we have some very small percentage of magnesium oxide, or MgO, shorthand is M. Okay, so we should limit the amount of magnesium in Portland cement because they may cause some problems, such as so-called unsoundness, which means the magnesium oxide will react with water. We have magnesium hydroxide, so that will affect the performance of concrete. So we should limit amount of magnesium oxide to less than 5%. Okay, but the major four is calcium oxide, silica, alumina, and ferric oxide. Carbon dioxide is also very minor. Okay, it's CO2. The shorthand is C with a dash on top. water, H2O, the shorthand is H. Okay. And the sulfur trioxide, it is not necessary in concrete, but it is typically will represent in small percentage in concrete, in cement. So that is SO3, and the shorthand is S with dash on top. Okay, so try to remember the shorthand for different type of oxides. All right. So this is another important slide showing us typical cement composition, also called compound. Okay. We have tricalcium silicate, which has 3 parts of calcium oxide with 1 part of silicon oxide. Okay. The shorthand is C3S. Okay. Remember C here represent CaO and S here represent SiO2. Okay. So C3S is actually tricalcium silicate. Okay. 3 parts of calcium oxide with 1 part of silicon oxide. Okay. So take about 50% plus minus. We also call that C3S E-light. E-light is C3S with a small percentage of impurities in it. Okay. So when we talk about E-light or C3S or tricalcium silicate, basically they means the same thing. Okay, so that's many different names for us today. Okay. The second one, dicalcium silicate, also called B-light, is 2 parts of CaO with 1 part of silicon oxide. Shorthand is C2S. Third one is tricalcium aluminate, 3 parts of calcium oxide with 1 part of silicon. So the shorthand is C3A. Okay. The fourth one is tetracalcium aluminum ferrite. Tetra means 4, so we have 4 parts of calcium oxide with 1 part of aluminum oxide and 1 ferric oxide. So shorthand is C4AF. Okay. And don't forget gypsum. So gypsum is calcium sulfate with 2 parts of water. The shorthand is CSH2. Okay, so these 5 are the 5 major compounds in modern cement. Okay, don't confuse the compound with oxide. Okay, so this is called oxide or constituent materials. Okay, and this is called compound. Okay, so compound is made by 2 or more type of oxide. Okay. Okay, so when we have a clinker in hand and we want to know the percentage of this compound. Okay, because different type of cement, the percentage of this compound are different. So how we can calculate or how we can analyze the percentage of different compound in the clinker? Okay. So direct analysis of compound composition is very complex and also time consuming and expensive. Okay. But we can use an easier way, which is combination of XRF, which is called X-ray fluorescent spectroscopy. So using this method, we can quickly know the percentage of oxides, including calcium oxide, silica, alumina. Okay. So inside the clinker. And then we can use some equations to estimate the compound, which is C3S, C2S, C3A, and C4AF. Okay. Right. So the purpose of this calculation is called bulk calculation, is to calculate or estimate easily the percentage of this compound based on XRF, based on the chemical analysis, by knowing the oxide percentage. There are some assumptions to use bulk calculation. So you can just read from here. You don't need to understand the details why, but you just remember we have some assumptions when we estimate the percentage of compound based on bulk calculation. Okay. And you should definitely know how to calculate the compound percentage. Use these equations. Okay. Depending on the ratio of A to F, this is ratio of aluminum oxide to ferric oxide. If that ratio is larger or equal to 0.64, we use this set of equation. For example, the percentage of C3S is equal to 4.07 times C. C is percentage of calcium oxide from XRF. Okay, so you can just use this equation to estimate the percentage of these compounds. We call that case A. If that ratio is less than 0.64, we use another set of equation. Okay, so very easy to use the bulk calculation, but it may not be very accurate, but it's very convenient. Okay. All right, so here are some more details about bulk calculation. Okay, so for example, the relative proportion of C3S and C2S are sensitive to percentage of calcium oxide, and also the calculate C3S percentage is low compared to what we actually measured by using XRD, if we do, and some other notes, but again, this is very details. You do not have to understand and remember that. Okay. Just for your information. So this is one way to calculate or estimate the percentage of the compound. Another method, we can use photomicrograph. Okay. For example, we get sample of clinker, and we cut a thin slice of that clinker and take a picture of the clinker and watch it studied under a microscope. Okay. Because different compound has different color and shape. For example, C2S has this dark and round shape, and C3S has this angular and light color shape. Okay. And everything in between actually is a mixture of C3A and C4AF, the other two major compounds. Okay, so by studying the picture, we can estimate the areas for example, C2S by counting the pistons in the pictures. So based on number of pistons, we can estimate the area percentage of different compound, and based on that, we can estimate the weight percentage of compound. Okay, so that's the general idea using this method. This is a real picture of the clinker. So that's the polished thin section of clinker. So again, the dark round color is C2S. Okay, the angular shape and yellow light color is C3S, and everything in between is a mixture of C3A and C4AF. Unfortunately, we cannot tell which part is C3S and which part is C4AF. We call that liquid phase, but we can know roughly how much C2S and C3S we have. Okay. The picture on the right shows us a scanning electron microscope, or SEM. In the later part of this class, we're going to talk about SEM, XRD, this technology to study the materials. So using SEM, we can see magnified picture. This is 3,000 times magnification of C3S. So these are crystals. Right. We can also use XRD, and this is XRD to study the different compound. XRD is like a fingerprint for different type of crystals, such as C3S and C2S. They have different shapes of these peaks. Okay, so based on the shape of the peak and also the height of the peaks, we can somehow know what type of crystals in the samples and even the percentage of these samples. Okay, so this is called XRD. All right. This is another picture of XRD. So A is the peak for A light or C3S. B is for B light or C2S. Okay. Some of the peaks of A light and B light are overlap, so make it very difficult to quantify the percentage of this compound. Okay. All right. So more details about XRD. It is easy to tell what phases are in the sample, but what are the percentage or how quantitative analysis is very, very difficult. But nowadays we can use the so-called rate-weight method to estimate the percentage of different compound under the help of computer software. So nowadays it is still possible to do the quantitative analysis of compound using XRD. Okay, and sometimes we need to separate different phases before we do the test. Okay, again, this is very detailed information, just for your knowledge. Here is the picture of cement grains. Typically, cement color is gray color or yellowish color. Okay. This is under microscope, 50 micrometer. You can see the angular shape of cement grains. All right. So we cover most part in this class. Okay. First of all, how does concrete compare to steel and wood as the building materials? Okay. What are the strengths and weaknesses of concrete compared to steel? Okay. And the concrete must be understood at what scales. We need to understand concrete in microstructure or from the chemical point of view to better understand the chemical reaction, so we can better understand design and control the concrete in the micro scale. Okay. We also learn what are the raw materials used to produce cement. Raw materials basically LISA or LISA. Okay. And what are the major compounds? C3S, C2S, C3A, C4AF. Okay. What are the shorthand for this oxide? What's the difference between the oxides or the constituent materials and compound such as C3S? We also learn how to use bulk calculation to calculate the percentage of the compound based on the percentage of oxide from XRF. Okay? And lastly, we study how to quantify the percentage of a compound based on XRD, or study the picture of the clinker. Okay, so these are some reading assignment. There's no homework for today. Okay, so that's the end for today's lecture.